Simple harmonic motion is a special type of periodic motion. To understand what it means, we consider mass spring system as an example. It is a mass attached to a spring oscillating on a horizontal frictionless surface. What force is responsible for oscillating motion of mass spring system? When the block is pulled away from its equilibrium position, spring is stretched. As the block is released, spring force pulls it back to equilibrium. Because of inertia, it overshoots in the opposite direction, thus compressing the spring. But spring force slows the block down and then again pulls it back to equilibrium position, and this to and fro motion continues. Notice that when the spring is compressed, it pushes the block to right, and when the spring is stretched, it pulls the block to left. In either case, spring tries to restore the system back to its equilibrium position. Force that tends to bring a system back to its equilibrium is called restoring force. And here, elastic force of spring is the restoring force. Note the relation between force vector in blue and displacement vector in black. At bigger displacement from equilibrium, force is more. At smaller displacement from equilibrium, force is less. At equilibrium, force is zero, which makes sense because at relaxed length, spring does not push or pull. From this, we can conclude that restoring force is proportional to displacement, and simple harmonic motion is defined based on this relation between restoring force and displacement. Any periodic motion that is result of a restoring force, which is proportional to displacement, is called simple harmonic motion, SHM for short. In other words, acceleration of simple harmonic motion is proportional to displacement. Note that this is a non-constant acceleration. It is changing as displacement changes. Let's look at the situation mathematically. Restoring force is proportional to displacement in SHM. Restoring force in this system is provided by spring, so replacing F restoring with F spring. So far we have written the relations in terms of magnitudes. Let's incorporate direction. When block is to the right of equilibrium, restoring force is to the left. Similarly, when the block is to the left of equilibrium, restoring force is to the right. So this proportionality, written in terms of vectors, must include a negative sign. Obtaining an equation from this proportionality means we write a proportionality constant. Spring force equals negative of spring constant K times displacement. This equation is known as Hooke's law. When relating only magnitudes of spring force and displacement, we drop the negative sign. If we look at motion graphs of objects undergoing SHM, we notice that they have a sinusoidal shape. Here, position versus time graph is a sine curve, and force versus time graph is flipped because of opposite directions of force and displacement. Simple pendulum is another example of simple harmonic motion. In ideal case, it is a mass attached to a frictionless pivot through a massless string. It oscillates in an arc and air resistance is ignored. What force is responsible for oscillating motion of a simple pendulum? When massive bob is displaced from equilibrium position and released, tension in the string and weight of the bob do not act along the same line, and they do not add up to zero. Weight is constant and points downward, but tension changes direction as well as magnitude. Restoring force for the motion of a simple pendulum can be figured out by drawing free body diagrams of the pendulum. We can break the weight vector into components, one parallel to the string and other perpendicular. Weight component along length of the string is opposite to tension. Weight component perpendicular to the string tends to bring the bob back to equilibrium. Here it is pointed to left. Here as well. When pendulum is swinging to left, this component would point to right. Thus, weight component perpendicular to the string provides the restoring force here. Also note that when displacement of pendulum increases, this component of weight perpendicular to the string also increases, which indicates that this is a simple harmonic motion as restoring force is increasing and decreasing with displacement. Let's look at the situation mathematically. We look at the geometry of the situation. This angle between string and a vertical line is theta, and it is the same as the angle between the string and weight here. So this weight component perpendicular to the string is Fg sine theta, which is the restoring force. M and G are constants, so we can write the equation as proportionality. Restoring force is proportional to sine theta. Here theta represents angular displacement. This is not exactly the condition for simple harmonic motion. SHM requires that restoring force be proportional to displacement, not sign of displacement. So is pendulum motion SHM or not? Well, if the angle is small, then sine theta value is very close to theta. Now restoring force is proportional to displacement and simple pendulum satisfies the criteria of SHM. Here it's important to understand this approximation. Sine of a small angle approximately equals value of the angle only when the angle is in radians. For example, consider a small angle for oscillation of pendulum, say 15 degrees. 15 degrees equals 0.262 in radians, and sine of 0.262 equals 0.259. 0.262 angle value, 0.259 sine of the angle, pretty close. But the condition is that the angle has to be small and should be in radians. So the conclusion of all this explanation is that simple pendulum undergoes SHM for small angles because restoring force for small angles is proportional to displacement. We saw earlier that motion graphs of objects undergoing SHM have a sinusoidal shape. This holds true for simple pendulum as well for small angles. By small angles, I mean angles less than 30 degrees. As the pendulum swung to and fro, we obtained this graph of angular displacement versus time, and it has a sinusoidal shape. For comparison, let's look at displacement versus time graph for large angles. Here, orange-colored oscillating bob and graph are representing what is expected of the pendulum if it undergoes SHM. The purple-colored graph is showing the actual motion of pendulum at large angles, which is oscillatory but not matching the sine curve at all. So pendulum motion is not simple harmonic at large angles.